So we've talked about the Lewis model for bonding, and it is an oversimplification. We know that. It's still very useful for a lot of things, though. More advanced models apply quantum mechanics to molecules. So there are a couple of different theories involving quantum mechanics. These modern quantitative approaches can accurately predict a lot of things like bond length, bond strength, molecular geometries, dipole moments of molecules, all sorts of things. That involves a lot of math and isn't needed for our purposes. So we're going to look at two of the theories in a qualitative manner. So we're not going to deal with all the numbers and calculations. We're going to just look at the ideas, basically. So the first one is called valence bond theory. So we learned that electrons reside in quantum mechanical orbitals on individual atoms. And we talked about the different levels, principal energy levels, the different sub-levels, and then on each sub-level, the individual types of orbitals. So the standard atomic orbitals, S, P, D, and F, remember those kind of funky balloon shapes from the book? S orbitals are spherical, P orbitals are sort of dumbbell shaped, and the rest of them are just too crazy to mention. So that's on an atom. So if you put two atoms together in a molecule, valence bond theory says, instead of just looking at those individual orbitals, let's look at hybridizing the atomic orbitals, blending two or more standard atomic orbitals to form a differently shaped orbital. So the idea here is that when two atoms approach each other, the electrons of one atom are attracted to the nucleus of the other atom. And valence bond theory is looking at the energy changes resulting in those interactions. If they get too close, then they begin to be repelled by each other. So valence bond theory says a chemical bond will form if the energy of the system is lowered by the interaction, because that's all of nature is going towards lower energy. So here we have a graph showing energy. Come on, pointer. Okay. Energy going up here. This is 0, so this is positive energy, which would be unstable. This is negative energy, which is going to be more stable. And we're looking at two hydrogen atoms approaching each other. So here we have the distance between them. They're never going to be able to completely touch each other, but here they're far away. So if we go this way and look at them getting closer. Yeah, pointer froze up. So the two atoms begin, when they start to get closer to each other, they begin to have some attraction for each other, and that lowers their energy. When they're far away, their energy is 0. As they get closer, the energy decreases. Let's see if I can get that pointer. Oh, I'm just totally screwed, I think. Oh, no. So as the atoms get closer together, their energy decreases. And this continues until we hit a minimum energy, whatever, down there at the bottom of the curve. Thank you, train. Yeah, needed that right now. Okay. Then as those two atoms get closer together, now the repulsion of their two nuclei for each other begins to come into play, and the energy goes back up. So you can imagine a ball rolling down a hill, and it's going to settle at the bottom there. As these two hydrogen atoms come together, you can sort of imagining them coming together, and oh, wait a minute, that's a little too close, back up, oh, that's a little too far, let's find the exact right spot. It's a little bit like two people, right? You ever had a conversation with a close talker? Somebody who's just a little too close for the extent of your relationship, right? It's like, just back off just a little bit, and you back up and they keep following you, and it's really awkward, right? There is that sweet spot of a perfect distance, right? And what that distance is going to depend on the molecule, depend on the atoms, but this is what valence bond theory is looking at. What is the overlap here where the energy is at a minimum? So the interaction energy is usually going to be negative, which stabilizes, when those interacting orbitals contain a total of 2 electrons that can spin pair, meaning they can orient with opposing spins. Because how could you have shared electrons attracting these things together when those electrons are repelling each other, right? Because they're negative charges. So that's where the spin comes in. And it's a lot more complicated than this, but you can just sort of think of it as, well, when they're opposite spins, then they're okay to be close together. It's not that they change their charge, they don't become positive or anything, but when they're spin paired, then they're okay to be together in an orbital. So typically what happens is we have 2 half-filled orbitals, 1 electron in each orbital, and those come together and overlap, and you have a pair of electrons being shared. That's a covalent bond. Sometimes you can have a filled orbital with 2 electrons on one atom overlapping with an empty orbital on another atom. So you still have 2 orbitals, but this time both electrons come from the same atom. That's called a coordinate covalent bond. So the 2 atoms with their half-filled orbitals approach, the orbitals begin to overlap, and the electrons align with opposite spins. A little bit like what happened in the quantum hotel, right? So they're going to be in the same bed, so one sleeps right side up, one sleeps upside down, and then they're okay. So the big ideas here: valence electrons of atoms in a molecule reside in quantum mechanical orbitals. A chemical bond results from the overlap of 2 half-filled orbitals in which those 2 electrons spin pair. The geometry of the overlapping orbitals determines the shape of the molecule. Any questions so far? Okay, so let's look at how these orbitals could overlap. So here we're looking at dihydrogen sulfide, so a sulfur atom and 2 hydrogen atoms. And if we look at the orbital diagrams for sulfur and for hydrogen, hydrogen, of course, has 1 electron, so it's got that half-filled 1s orbital. The diagram for sulfur shows that there are 2 half-filled 3p orbitals. So we could overlap these half-filled orbitals and see what happens. So we're going to take this orbital and overlap it with that one, take this orbital and overlap it with this one. So here are those balloon shapes. So we've got our p orbitals, there's 3 of them. They each have 2 lobes, right? So this is one, and this is another one, and that's the 3rd one. So this one was full already. That's this guy right here. And there's this s orbital in the middle, and that's full. So this one had 1 electron from sulfur, and this one had 1 electron from sulfur. And so we imagine the s orbital from the hydrogen with its 1 electron overlapping with the half-filled orbital from sulfur, and that forms a bond. And then this hydrogen overlaps with the other half-filled p orbital, and that forms a bond. That make sense? So that would predict that the bond angle here is 90 degrees, right? Because that's the angle of those lone pairs, of the p orbitals. So the actual bond angle is 92 degrees. So that's pretty good, 92 versus 90. Vesper theory predicts that it's a little less than 109.5. So here Vesper theory seems to be a bit off. So far, so good. Let's look at something else. Let's look at carbon and hydrogen. So one carbon atom bonding with some hydrogen atoms. So here's the orbital diagram for carbon, and we have a full 2s orbital and two half-filled 2p orbitals. Of course, hydrogen has half-filled orbitals. So we could imagine that a hydrogen will overlap with this p orbital. We can imagine another hydrogen atom overlapping with that one. And that would give us this thing right here. We're not showing that empty p orbital because it's empty. Okay? Does that make sense? We're just overlapping things on individual atoms. So that predicts a bond angle of 90 degrees. It also predicts a formula of CH2, because here you can overlap with only two hydrogens and then you're done. But this doesn't line up with observation like H2S did. Observed reality is that 4 hydrogens bond to the carbon and the bond angles are 109.5. So that tells us something is missing from our explanation here. So up to this point, we are assuming that the orbitals in the molecules are the same shape as the orbitals in the atoms. It's a reasonable thing to think, but it's not true. When two atoms bond to form a molecule, their orbitals can hybridize. They can become mixed together, sort of averaged together. So hybridization is a mathematical procedure in which you combine standard atomic orbitals to form hybrid orbitals. It's a little bit like averaging, but more complicated. These hybrid orbitals correspond more closely to the actual distribution of electrons in molecules. They are still localized on atoms, but they have different shapes and different energies than standard atomic orbitals, the SPDF that we learned about before. So hybrid orbitals minimize the energy of the molecule by maximizing the overlap. The better the overlap, the lower the energy and the more stable the molecule. Hybrid orbitals give you better overlap because the electron probability is more concentrated in a single directional lobe rather than distributed equally on both sides of the atom. Hybridization does require energy, sort of requires an investment, and it will only happen if there's a payback, a lowering overall in energy, so that you get out more than you put in. We're going to focus on the interior atoms and assume that the terminal atoms are unhybridized. That's not true, but we can do that in Chem 1A. Atoms that form more bonds are more likely to hybridize than atoms that only form, 1 or 2 bonds, which is typically the case of those terminal atoms. They've only got 1 bond. So some general statements about hybridization to keep in mind. The number of standard atomic orbitals that you add together is always going to equal the number of hybrid orbitals that you get. So you could think of it as orbitals are conserved. If you take 2 orbitals and you combine them together, you're going to get 2 hybrid orbitals. If you combine 4 orbitals, you're going to get 4 hybrid orbitals. What combination of standard orbitals you put together is going to determine the shape and energy of the hybrid orbitals. And the type of hybridization that occurs is the one that's going to yield the lowest overall energy for the molecule. Well, calculating that is rather complicated, and we don't want to go there. We don't need to go there. So instead of doing calculations, we're just going to use Vesper theory to help us predict the hybridization. That works pretty well for most things. Okay, so let's look at the first hybridization. And this is the one that explains methane, CH4. So here we have the standard atomic orbitals for carbon. There's the 2s, and there's 3 2p orbitals. And we looked at diagrams like this, and we said, well, this is the second floor of the hotel. There's two different rooms. This room costs more, and that's why it's up here. And we've got two electrons staying there. They each have their own beds, and this pair of electrons are sharing a bed, and they're there because it's lower in energy, right? So hybridizing is a little bit like tearing down the wall between the two rooms. So that picture doesn't work all that well for my purposes. So we could look at it this way. Well, I'm just going to use little boxes here to draw the beds. I'm not going to put, four posters on them and three-dimensional and stuff. I don't want time for that. This is the 2S room, and this is the 2P room. So the S room has one bed. The P room has 3 beds. And what we've got going on here is that we've got 2 electrons here and 2 electrons over there. So what hybridization does is it says, well, let's tear down this wall and just make this one big room with 4 beds. So we'll get rid of the wall. And this is just one big room. And now you can't charge more for one bed in this room than you can for the other beds. So all the beds cost the same now. So this guy's like, hey, I'm getting out of here. I'm going to go get my own bed. So now he can move over here. That kind of makes sense? It's my stupid analogy. We're taking these 4 atomic orbitals, and we're averaging them. We're combining them and coming up with 4 new orbitals from those original 4. They have different shapes and different energies. The energies of these are between the energies of the 2P and the 2S. So when I remodel this hotel room, the price is higher than it was for the 2S room, but it's lower than it was for the 2P room. It's in the middle. We say that these 4 orbitals are degenerate, meaning they're all at the same energy. Just like the hotel room, if you stay in this bed or this bed, doesn't matter what bed you sleep in, it costs the same amount to stay in that room. That makes sense? So let's look at the shapes of these things. So we're taking this shape, the S orbital, and these 3 p orbitals. So there are mathematical functions that describe those shapes. And what they're doing when they hybridize orbitals is you just combine those functions together. So it's a bit hard to visualize, but take these 4 things, you combine them together and get 4 hybrid orbitals, and they're each the same shape, the same energy, but their orientation is different. Just like these p orbitals had different orientations. They had the same energy and the same shape, but they were oriented differently. So now we have 4 orbitals oriented around the central atom. 4 things form a tetrahedron. So these 4 hybrid orbitals will form a tetrahedral shape. So because we're combining this sphere with this dumbbell shape, what we end up with is sort of a lopsided dumbbell, where one lobe is larger and the other is smaller. And that's the same for all of these. Because it gets really complicated drawing all of these, we typically just ignore the smaller lobe. So that's what's happening here. I like the author's use of color because if you mix blue and red, you get purple, right? So these are hybrid orbitals. Any questions so far? So if we draw an orbital diagram with those hybrid orbitals, now we see that we have 4 half-filled orbitals. They can spread out because those are all at the same energy, and so they will fill them individually first before pairing up. So now we have 4 half-filled orbitals, and each of those can overlap with a half-filled orbital on a hydrogen. So here we have our purple sp3 orbitals, and they're overlapping with hydrogens, and this gives us a molecule that matches our experimental observations. The formula is CH4, and the bond angles are 109.5. Because this is a combination of an s and 3p orbitals, we call it sp3. Any questions? You can have a lone pair in a hybrid orbital. The presence of that lone pair is going to reduce the atom's tendency to hybridize, but it'll still hybridize. So if we think about ammonia, let's draw orbital diagram, that's what it's called, for nitrogen. So there's the orbital diagram for nitrogen. And you could see these p orbitals overlapping with hydrogens, and that would give you the correct formula, but the geometry is not right. So what this actually does is it makes sp3 hybrid orbitals, where we have 4 equivalent orbitals, we call that sp3. And now when we put 5 electrons in there, we fill them each halfway, 1, 2, 3, 4, and then one of them pairs up. This is the lone pair. And these are the 3 half-filled hybrid orbitals shown here. And those can overlap with the hydrogen atoms and form bonds. Now this would have a tetrahedral shape, 109.5 degrees. But it's less than that because the hybridization is less complete because of the lone pair. So it's a slightly different explanation of the change in bond angle than Lewis or Vesper theory had. Any questions? So what about double bonds? Well, we don't have to take all 3 of those orbitals from the 2p sublevel. We can take the 2s and 2 of the 2p orbitals and put them together and leave this one alone. So if we're drawing the hotel, here we have the 2nd floor. And so there's the bed in the S room. And here's the 3 beds in the P room. So this remodeling, instead of just removing this wall, we're moving the wall over. Now, why would you want to do that? Well, we don't have to get into that. But it's like moving the wall over. So this gives us 3 orbitals here that are equivalent, and this one is left unchanged. So this room then is called SP2 because it had a bed from the S room and 2 beds from the P room, and this is just P. So we combine these orbitals and we get 3 hybrid orbitals called SP2, and this P orbital is left unchanged. So what would that look like? So we take an s orbital and 2 p orbitals, and you mash those together, and you're going to get 3 of these lopsided dumbbell things. But there's 3 of them, and so they're going to arrange like 3 balloons would and form a trigonal planar arrangement. Okay? So H2CO has sp2 hybrid orbitals. So here are the atomic orbitals. Here's carbon, oxygen, and hydrogen. Let me just draw the structure, Lewis structure here real quick. It's not a double bond. So carbon is the central atom. We're going to look at hybridizing carbon's atomic orbitals, but we're not going to do anything to the hydrogen or oxygen orbitals. So here we've got the carbon. What we can do is we can take an S and 2 of the p orbitals and leave 1 p orbital out. So we're taking this arrangement and we're making that. Now, why does that electron go up there? Well, the difference in cost now between these two rooms, because by combining these, you've raised the cost of the S, lowered the cost of the P, so it's kind of in between. The difference in energy here is small. But the attraction of having your own orbital outweighs the small difference in cost. And so these 4 electrons can spread out and each have their own orbital. So single bonds will form as the hydrogen overlaps with the oxygen. And there's 2 hydrogens. They didn't draw the other one. So that's going to overlap with one of those. And then the oxygen has 2 half-filled orbitals. One of those will overlap with that sp2 orbital on carbon, and the other will overlap with the unhybridized p orbital. And you might say, well, why didn't it do sp3? You'd still have the right combination, but the geometry wouldn't work. How's that for a picture? Right? I will try to explain these to you. So here's our carbon. These purple orbitals here are the hybrid orbitals sp2. There's 3 of them, right? And so they're going to form this shape where they're spread out in a trigonal planar manner. Each of these has 1 electron in it, so this overlaps with a hydrogen to form a bond. This overlaps with this hydrogen to form a bond. This overlaps with a p orbital on the oxygen to form a bond. The unhybridized p orbital is going straight up and down. It's perpendicular to the hybrid orbitals. And this oxygen also has a perpendicular p orbital. This is half-filled, that's half-filled. These 2 can overlap. Now they do so in kind of an awkward sideways manner. Remember that in this p orbital, the electron is on both sides of the nucleus at the same time, because it's a wave, right? It's a wave, and so it's not that the electron is just up here or just down there. It's in both places at the same time. And so what we have is an overlapping of that wave function. And so we get a bond. It's a single bond, but it occurs above and below the internuclear axis. Any questions yet? It's a little weird. There are 2 different kinds of bonds here. These are called sigma bonds because they overlap end to end. And this is a pi bond. It overlaps side to side. So if you imagine this bond, and let's say you're looking from the oxygen down to the carbon. So on the carbon, you see the outline of that orbital, and then the oxygen, you see the outline of a similar orbital. They overlap each other. And so as you're looking down that axis, it looks like a sigma. It's circular. It's symmetrical. This p orbital is a side to side, and so you can imagine that as tip your head to the left as a sideways pi. Side to side overlap. That's how I remember it. So sigma orbitals are sigma bonds are overlapping end to end, and pi bonds are overlapping side to side. This is not as good. It's not as it doesn't lower the energy as much. So let's look more at that pi orbital. the pi bond, I mean. So pi bond happens when you have p orbitals that are overlapping side to side. So here we have half-filled either py or pz orbitals. So they are parallel with each other, and they will overlap side to side. You can kind of imagine it going like this, kind of mushing together. So you get this. The other p orbital is the px, and that is lined up along the axis between the two atoms, and so those would overlap end to end and form a sigma bond. There's an overlapping end to end. So there's sigma bonds and pi bonds. So we can label each of these bonds, and the notation tells us what kind of a bond it is, what atoms it's bonding between, and the orbitals that are overlapping. So what we've got going on here, this is our Lewis structure. This is sp2 hybridized, and so each of these bonds are a sigma bond between sp2 hybridized orbital on the carbon atom and the s orbital on the hydrogen. This bond here is also a sigma bond end to end with a sigma, and it's between an sp2 hybrid orbital on the carbon and an unhybridized p orbital on the oxygen. This bond is the pi bond side to side, and that's the overlap between a p orbital on the carbon and a p orbital on the oxygen. Pi bonds are always the overlap of p orbitals. P orbitals, pi bonds, right? Pi is the Greek letter P. So valence bond theory gives us more insight than the Lewis model does. Valence bond theory tells us that the double bond between the carbon and the oxygen is actually two different kinds of bonds. It's not two identical bonds. And what we observe is that pi bonds are weaker than sigma bonds because the overlap is not as good. Right? It's a side-to-side overlap. It's less efficient than the end-to-end. And those pi bonds are easier to break. So if you're going to break a bond, one of those double bonds will break first, and it will be the pi bond because it's weaker. Valence bond theory also explains why double bonds cannot rotate. So here we have dichloroethane, and there's a single bond between these two carbon atoms. The single bond you can rotate. It's like sticking your fingers end to end, and you can rotate your hand, right? It can like swivel, right? In a pi bond, that's like sticking two fingers together. And now if you try to twist one hand, you can't do it without breaking that bond. Because this bond is overlap above and below the axis. And so you can't twist one without twisting the other. So these two structures are the same molecule because there's free rotation around that single bond. These are two different compounds because they cannot rotate. You can't take this cis 1,2-dichloroethane and make it into trans 1,2-dichloroethane without breaking bonds and making bonds, and that would be a chemical reaction. So these are actually two different compounds. So what about a triple bond? Because I know you were asking, you were thinking that in your head, right? Well, in a triple bond, you take an s orbital and one of the p orbitals, and you hybridize those, and you leave two unhybridized p orbitals. So now, when we overlap or hybridize the s and the p, again, we get these two purple lopsided dumbbell things, but now they are oriented in a line opposite of each other. So if we look at acetylene. It says draw the Lewis structure. Well, it's kind of anticlimactic. It just looks like this. It's not really that much different. So this carbon has a single bond with a hydrogen, and this carbon has a single bond with a hydrogen, and then the two carbons have a triple bond with each other. So this is going to use sp2 hybridization. So each of the carbons is going to form an sp hybridization. I said sp2, I meant sp. And then there's two unhybridized p orbitals. So this one can overlap with a hydrogen, and the other one can form a sigma bond with the other carbon, and then these two half-filled unhybridized orbitals can overlap side to side and form 2 pi bonds. That looks like it could be fun, like as a pool float or a lake toy or something, right? You can imagine doing something with that. So there's the carbon, and it has 2 orbitals that are hybridized. And so they're going to be in opposite directions, each having 1 electron. So this one will overlap with the hydrogen. This one will overlap with the same type of orbital on the other carbon. Here we really have 2 internal interior atoms, and so we have to look at both of them as hybridized. This carbon will also have an sp orbital that can overlap with the hydrogen. And then we've got 2 pi bonds. There's this one that's above and below, and there's this one that's in front and behind. This is consistent, the shape of this is consistent with energy and with Vesper theory. Experiment and Vesper theory.